Hello and good morning and welcome to this focus session on thermal and acoustic metamaterials. I'll just briefly introduce myself before as session chair. My name is Pete Hobson. I'm one of the scientists at Kinetic, and it's my pleasure to be the session chair today. Shortly, I'll introduce our three distinguished speakers who will be talking in turn, and if there's time, I'll also give a short presentation at the end. So the concatenation really of acoustic and thermal metamaterials is quite interesting to me because they are in some respects both disparate and similar at once. They're disparate because I guess at one fundamental limit, thermal metamaterials are concerned with photons, whilst acoustic metamaterials are concerned with sound waves and air. But at the other fundamental limit, we of course all recognise that heat transfer in all media is mediated by vibrational modes or phonons. Another similarity that we've certainly noticed looking at different problems in Kinetic is that thermal and acoustic challenges that we see in the real world often have the same source. So air breathing engines have both sort of mechanical aspects that generate both heat and noise. And the challenges for the materials are in some respects similar. Conventional acoustic and thermal materials for preventing damage through heat or sound, often very thick, very sort of traditional materials. We all think of things like rock wool. So there's definitely a strong need for us to come up with new material solutions that can block both sound and heat in thinner layers, and also play new games such as divert energy into new directions or concentrate it. So this is where acoustic and thermal metamaterials come in, and we all hope and expect that this exciting new area to generate new applications and products. We're lucky today to have three distinguished speakers, very much sort of Renaissance men of the metamaterials area. I'm going to introduce them all in turn. Those of you looking at the webpage, first of all, I should just flag up a slight change to the published schedule. Our first talk will be by Daniel Elford, who's CTO, co-founder at Sonobex Limited. Daniel is also a visiting academic at Loughborough University. So unfortunately, although we don't have Daniel's biography on our webpage, he's also talking in the built environment and construction areas, and so you'll be able to read all about him on the splash pages for those areas. So Daniel's going to kick off with his presentation. The majority of the questions will be saved to the end, and that's because we're just filtering them from different applications here, and it's just more practical for us to measure and to manage it like that. So without further ado, I'd like to invite Daniel to give his talk.
Nice, thank you, Pete. I'll just share my screen now. And hopefully you can see that. So my name is Daniel Elford from Sonobex Limited, and we were a spin out from Loughborough University in 2012. The focus of my talk today is low frequency attenuation with natural ventilation. And this is basically describing our new range of acoustic metamaterials that we utilize for industrial noise control and other applications. So I'll start by just giving a little bit of an introduction about us. So yeah, we're an award-winning spin-out company from Loughborough, like I say, but we are an engineering noise control company that uses innovative noise control solutions. And we invented a technology called Noise Trap, which is our metamaterial-based solution. And we have a mantra of using new disruptive acoustic technologies to solve low frequency noise problems, because sound should not hinder anyone. And Sonovex are part of a larger group company based out in the Netherlands, so Elford Group, which is made up of 5 different divisions, but all heavily involved in different types of noise control and acoustic materials. We're 65 years old this year, and that's quite a good year, seeing as the first piece of noise legislation was actually put in place in the UK in 1956 as well. So we're very well averse to knowing how to treat different types of solutions in the market. And here's just some examples of the typical projects we deliver using standard materials. This is actually a noise enclosure which got installed in the centre of Amsterdam's train station. We also do things like anechoic chamber using different types of standard acoustic materials. And we also do sort of residential, office, commercial spaces in terms of improving acoustics. And we have a division that also develop and design special doors for different types of architectural acoustics and other conventional sound problems. But the thing to highlight with all of those types of solutions in our group companies is that they all currently use the conventional approach to treat noise. And this is where Metamaterials come into their own, because conventional acoustics, the acoustical performance that you achieve in the real world is all to do with the material properties of the solution you're installing. So in terms of acoustic, 2 main aspects govern the acoustic performance, which is transmission loss, which is effectively stopping sound, and then you have absorption as well. Key thing to highlight is with both of these aspects, it is very difficult to mitigate or reduce noise at low frequencies due to this material limit, basically. All standard acoustic materials work much better at higher frequencies than they do at lower frequencies. And what usually you find in the market is a brute force approach where you use heavier, thicker, more mass objects to block low frequency noise, which in turn it means it's more costly and not a great solution for low frequency noise. There's a secondary issue with low frequency noise as well, because that travels further, it contains more energy, so you get more and more noise complaints from low frequency noise than you typically do at high frequency. So this is where we've started to use metamaterials. I won't repeat the standard definition, you've probably heard it a lot today during this conference, but I used to say these have acoustic properties not found in nature, but there was a very recent publication where they managed to work out that a moth's wing was actually a type of acoustic metamaterial. So I've had to change my definition slightly. But in short, a metamaterial is governed by its geometric structure rather than their physical or material properties. And what we do at Sonobex is basically alter and tailor and optimize a coupled resonating system to enhance acoustic performance in the frequencies area of interest that we really want to target. And that's where the difficult noise problems come in. So what we developed at Sonobex is we call these noise trap panels, but these are effectively an acoustic metamaterial based acoustic panel system, which we can build enclosures, screens, and the standard type of acoustic solutions from this new type of technology. What's very beneficial about this technology compared to conventional solutions is that we get very high performance in the low frequency bands in terms of its transmission loss. And also we get perfect absorption in target frequencies, which our metamaterial is designed for. So we have superior performance, and because a metamaterial is not based upon the material inside it, we don't actually have any acoustic infill or mineral wool to give you acoustic performance, which is standard in conventional noise solutions. And what also enables us to do using these metamaterial structures is actually we can allow passive ventilation through our acoustic panels to give cooling and thermal comfort into buildings or machinery enclosures. And because you have no mineral wool inside of these panels, what typically happens if a mineral wool based panel gets wet, it will actually reduce its acoustic performance in the real world, and the actual mineral wool will degrade quite quickly over time as well. Where our constructions, we actually make these completely out of steel with no mineral wool inside. And the reason we still use steel is because these get installed into industrial environments. We could actually make these out of any rigid material, such as plastics, for example. And I touched on the no acoustic infill properties of these panels. These has additional benefits. For example, if you're installing a noise enclosure around an industrial piece of machinery, a conventional acoustic panel with mineral wool inside will actually act as a thermal insulator, causing your asset or the machine inside the enclosure to heat up. And in some cases, you can actually have breakdowns due to thermal overload. I mentioned about the through life performance. So the acoustic performance of our panels is the same on day one as it is 30, 40 years later in terms of its lifespan. There's no acoustic material to degrade inside our panels, which also infers the fact that you don't need to weatherproof our system as well. A lot of acoustic or noise enclosures are fully weatherproof to protect the rock wool or mineral wool inside those enclosures. We can also use these type of panels as well for really difficult environments, so food preparation, clean rooms and hospital environments, because there's no risk of fibre ingress into, say, an operating theatre or something like that, which is a really key benefit of having no acoustic infill. And it also makes the panels very, very easy to clean. There's nothing to absorb, dirt, chemicals, and things like that. And it's very easy to clean the panels because you can literally just pressure washer them down without actually damaging the acoustic performance of the system. And there may be a big issue in terms of conventional acoustic solutions. The European Parliament are actually discussing at the minute an EU-wide ban on mineral wool-based solutions due to the possible health impacts of that. They're actually almost linking it to similar effects to asbestos. And is this a hidden problem with mineral wool being everywhere, basically, at the minute? And what we have from our panels, we've actually managed to develop a series of acoustic panel systems that we can build enclosures for, which have a different range of performances with targeted frequencies, depending on the machine for application. One thing we look at here at Sonobex is we're heavily involved in the power generation, transmission and distribution markets. And 100 hertz frequency of noise is a very key common problem where we have superior performance compared to conventional based solutions in these low frequency regions. So this makes it a very good fit to apply metamaterial based panels into industrial sectors for the benefits I highlighted on the last page, but also I want to focus on the naturally ventilated enclosures because we can provide passive ventilation with no acoustic weak points as well in an enclosure design. All of our results are fully independently accredited as well in terms of the transmission loss and the absorptive performance, and we can happily share results if people want to look at those. And to put it into perspective, this is basically a comparison from our metamaterial based panels on the left to a conventional based panel on the right hand side. And I just want to highlight some key numbers on here. So with our LF250 panel at 100 hertz, we get 34 decibels attenuation, where a conventional panel on the right here only achieves around 23 decibels. Things to note is what the panels are made from. Ours is carefully and cleverly folded sheet steel. The panel on the right here is actually made up of a sheet of perforated material. You have two 50 mil thick pieces of mineral wool, 2 sheets of plasterboard, another sheet of mineral wool, 2 more sheets of plasterboard, and then a sheet of steel on the back. And this conventional solution weighs 113 kilograms per meter squared, where our panel is only around 53. So we get much better low frequency performance with half the mass and half the thickness of our panel in this case. And another thing to highlight here is the RW value. This is basically the overall performance across all frequencies of our panel. And what you have in terms of a traffic noise weighted spectrum, you -2 from the 44 to get 42. And the panel on the right, you have 52 -10, which gives you 42 as well. So across a broadband sound application, they're equivalent performance, but we have much better enhanced performance at low frequencies. So I just wanted to show you some case studies and real world applications of these. They're just some nice pictures of the enclosures, but these are all low frequency noise problems that also required some sort of ventilation, where we installed our noise trap panels here. This is a very large electrical generator connected to a steam turbine, and there was a 100 hertz noise problem in which residents were complaining about. And for this client, it took nearly 5 years to find a robust solution for this. And the Sonovex metamaterial based panels was actually put forward and installed last year here. Another example here is actually for some blowers at a wastewater treatment works, a similar type of problem where there was residential complaints of low frequency noise. And again, we installed our LF150 noise trap panels here to mitigate that low frequency noise, but it also gives you that broadband performance I talked about. This is actually a freestanding barrier project installed at electrical substation. And the freestanding barrier here worked very well in this circumstance. You didn't need to move to a full acoustic enclosure due to the high absorption properties that we have. So if a noise barrier can effectively absorb frequencies, it will actually stop some of the sound leaking over the top of the barrier to give you enhanced performance compared to a standard reflective type noise barrier. And this is one of our ventilated noise trap panels. This is, again, another electricity substation in London. And what they had here on this site was 4 transformer bays contained within a concrete built building. And the big issue with this project here was the thermal cooling of the transformer inside these concrete buildings. The client here had another solution proposed, which needed mechanical ventilation system, acoustic chimneys, and then they also blocked up the front of this enclosure to stop the noise leaking, but that caused thermal overheating issues. So Sonobex actually developed a bespoke ventilated noise trap based metamaterial based panel, which sufficiently mitigated 100 hertz noise while still allowing enough cooling to cool down the machine inside. And we've had no problems in the last, I think, 5 years since this project's been installed here. And a key thing about enclosure ventilation, especially in the electricity distribution market, is that if the ambient temperature is increasing, your transformer assets inside a substation it's called a hotspot temperature. So inside the machine, it's increasing its own temperature, which then increases the relative aging rate of a transformer. And it's worth highlighting that over 15% of all breakdowns for transformers are due to overheating issues. So if we can adequately cool a transformer, you can actually prolong its lifetime without actually causing an issue in terms of the acoustic noise. What usually happens in a conventional noise enclosure is you have up to 1% of the area is defined by a small grill or ventilation section. And we've heard about some distribution operators actually opening doors on noise enclosures to allow for cooling of the machine, because it does create an issue, especially with mineral wool-based panels. And I will end on a slide that just talks about, it's a project from Electricity Northwest Limited, where they started to investigate passively cooling transformer asset, which allows us to be able to increase the load on the electricity network. There's going to be more and more energy moving to electrical services in terms of the energy transition. So this enables us to not overload, but increase the load on the network by allowing extra cooling to an asset to then extend the lifetime of currently installed transformers, for example. These pictures on the top left here was some of the solutions they come up with as part of that project, which just only answered the ventilation aspect. But you can see here, drilling holes in the wall actually caused a big noise issue as well. So we think we've come up with a very good solution, hitting that low frequency acoustic performance while still providing that passive ventilation for cooling of important asset machinery. And that brings my talk to an end. And that's my end slide there.
Daniel, thanks very much for a really interesting talk, and also, you know, combining thermal issues with the acoustic ones as well. That really sort of hits the mark in terms of our target here. Hopefully everybody who's been watching this has been filing some questions on the chat, which is on another app. We'll sort of sift through those at the end of the session, just so it's manageable. If I may, I just ask a question of you, Daniel.
Yeah.
I really like the ventilated sound traps. Many industrial grills obviously cut down the effective area somewhat of an aperture. What do you think is currently possible and may be possible in the future in terms of the airflow area for an aperture of a given size with an acoustic system?
Yeah, without preempting my talk that I have in the built environment and construction session, we can get equivalent open area to say a 50% standard acoustic louver. We have another product which we call noise trap blocks, which is a very specific ventilated solution whilst mitigating low frequency noise. So yeah, around 50% open area is the equivalent airflow we get, which is comparable to what conventional acoustic solutions have in the real world. Okay,
that's great. Thanks, Daniel. And once again, thank you for your talk. Massive virtual thunderous applause. Thank you.
Nice. Thank you very much. That's perfect.
So I'd like to introduce our next speaker today. Our next speaker is Dr. Gianluca Memoli, who is a founder and CEO at Metasonixx Limited. Gianluca is also an academic at the University of Sussex, UK. And so, Gianluca, please, the floor is yours.
Thank you. I'm trying to share my screen. Let's see if I manage to do that. Just 1 second. No, not this one. Looks like. No. Maybe let's go directly with this. And let me share this. Okay. Excellent. So, this is a session about noise and ventilation and how we can manage them together. And we heard already from Daniel that metamaterials are probably the solution for the future for this problem. Let me share with you something from my experience in this direction. So the need to reconcile what can be a conundrum between managing noise and managing ventilation is well known. This is a quote from a residential design guide which came out in January 2020 from a joint document from the Institute of Acoustics and the acoustic consultants in this country. So everyone knows that it's tricky. So it's not so tricky for the areas which are below 40 dBs, and these are the quiet areas, and according to the European Environmental Agency, they cover 30% of the population in Europe. It's equally not so, so it's determinant to manage noise for the people who are living in very noisy areas, because their noise has been connected to problems like cardiovascular disease or negative cognition effects. So these people, however, tend to keep their windows closed. And this leaves the rest of the population. And this, for these people, there is a negative impact on well-being, which can be measured in millions of hours of well-being left or lost to noise. For those people, you need a solution which can resolve and help them to resolve this conundrum. So do I close the windows or not? So if I have a noise outside, what do I do? If I have my friend in the office talking on the phone all the time, or on Zoom nowadays, if I have to design an apartment where for each blue arrow here there is actually a silencing solution to avoid the noise to get inside. If I have to manage a school where the pandemic now requires to keep the windows open and ventilation open even if there is noise outside. So we heard already something about the existing solutions, and so you can use attenuators for air conditioning, you can use louvers, ventilators, sometimes in schools. These are thick. You can use acoustic windows if you want to pay a premium. These are excellent, but they are all based on the idea that we heard Daniel mention earlier. You put mass or absorbers between you and the noise. Of course, the other solution is that you time. And so you can keep your windows open for a bit and then closed for the other bit. Is that live? So you have seen already Daniel telling you about their noise trap, and there are other, and here I have two other examples of UK companies using Metamaterials. One is KEF, we're putting Metamaterials behind their speakers, and the other one is ours. So the interesting bit about Metamaterials is that it's the geometry that determines the effect. So they are based on noise cancellation, and this allows the panels to be much thinner than traditional solutions. And as we heard earlier, in most cases, they also allow air through. So there is a lot of research, obviously, and you can see that the shapes are basically holes with a space around. So it's a bit like a flute, if you want, or a trombone, where there is a hole where the air goes through, and the other part, the box around, contributes to changing the sound, which also goes through. So you can have single resonators, you can have multiple resonators, but this is again something which is extremely sensitive to temperature. So that's why the solutions based on geometries which are not necessarily resonant are often more performant than others. So let me tell you about our experience at Metasonixx in this. So for us, building a metamaterial is a design effort. We start from poor materials, and then we discovered that you just need a set of predefined shapes that you can reassemble like Lego bricks, or just like you need 26 letters to do any words, you need just 16 shapes. And then you reassemble them according to different recipes to get the application. This allows to get to standard recipes, but also to custom recipes. And this makes our Sonoblind panels modular, just like if you were playing Tetris, because it's very easy to scale up. But also they make them much lighter than traditional ones, and we have seen some numbers from Daniel earlier. And also they allow air through. But the other important bit is that because they are modular, because our solutions at Metasonixx can be imagined in small bits that you can reassemble, they can be embedded in other products, and in some cases even tuned when you install them. We have some panels which let the songs of birds go through and not the rest of the traffic noise. So I want to tell you today about two of our panels, and one of that is this one, which is fully transparent, and the other one is this one, which lets 50% of the air through. So they are both based on the same idea. Part of the panel lets the sound go through, the rest of the panel creates a noise cancelling part, so it delays the sound so that when they are on the other side they cancel out. You can see that there is a large difference in weight for those two panels, and that will be crucial for deciding what you want to use in applications. So what we did is we installed our panels to test their performance. We installed them on a window, and we asked Anderson Acoustics, which is a noise consultant here in Brighton, to help us and to make an independent test of our performance. And I'll tell you why this is crucial again for Metamaterials. So we mounted the panel, you can see it here. We had the window partially open and partially closed, and they used a method which is traceable to an ISO standard. And what they get is a response which is basically flat between 250 Hz and 4 kHz. And the reduction was 11 dB. And the A means that we are weighting the dBs for the standard weighting that we give to perception. So 11 dB is clearly not sufficient to bring an high traffic noise to levels where there is quietness, but is determinant when instead you need to have a choice, and that's why we specialized in materials which are light and easy to move. The other bit is that the standard method of testing materials in acoustic is to put them in an impedance tube, which is basically a cylinder in which you put your material, and then you put a reflector at the end, you send the sound, and you listen to what changes when you put the material or not. and that didn't work for our materials. So we had to invent our own method, and we benchmarked our method with the measurement that you have seen in situ. So this shows that eventually we were then able to predict and design metamaterials based on some key points on calibration. But this also highlights the need for proper standardization in this field, because metamaterials, as you have seen, have incredible promises, but if we cannot compare them with the same tools that you do other materials, then it's a bit tricky. So I mentioned another panel where there is more air through, and this does 12 to 20 dBs. So it's specialized on a single frequency. It can also go up to 40, just like some that we have seen earlier. The point is the airflow and how you measure it. And again, that is an interesting point. What we are doing here is we have a box made with a metamaterial which is perforated, as you can see, in a special way. And we have a fan inside, and the fan lets some air through, and at the same time we are reducing the noise. So what we are doing is we are inventing, if you want, the way to characterize these panels to speed their application. So to end my turn today, I wanted to tell that the challenge of managing simultaneously ventilation and noise is well known, and not just in industrial setups, also in everyone's houses, in everyone's offices. So acoustic metamaterials might play a key role in solving it. Here we imagine a blind that you can pull down and block the noise selectively while letting the air through. Now, further work is needed on characterization methods for this type of materials. And also, in our case, for us as Metasonixx, we are testing now further designs, and the idea is to have different panels for different uses. So at the end of every talk, you should thank all the ones that helped. And Metasonixx is a startup from the University of Sussex and Bristol. We received funding from both the PSSC and the Innovate UK, and we had help from a lot of people who gave us advice on how to proceed, because as we heard in the plenary, that is an important bit. We need entrepreneurs, but also we need a substrate which helps them to kindle. Thanks a lot.
Gianluca, thank you very much for another very interesting talk. I hope again that as people have been listening in the portal, that we've been collecting many more interesting questions. Just briefly, I will ask, I really did like the transparent product. I thought that was a great aspect, and it's very easy to see perhaps how something like that might almost be used like a conventional secondary glazing screen to add acoustic or noise blocking functionality to a window. Obviously, plastics like that aren't as rigid as metal sheets. So, is there any limitations or particular challenges when using plastics to make these sort of metamaterials?
I think you can compensate for the material, or you can exploit, and that's much more interesting, the properties of the material to get a larger effect. So we are normally used to think of metamaterial as rigid objects, but I think there is an opportunity for exploiting also the non-rigid properties to participate into the managing of the noise. Did I answer your question, Pete?
Yes, you did. It was very good. Thank you very much. So thank you again, Gianluca, for an interesting talk. And now we'll move on to our third presenter. The third presenter is my colleague from Kinetic, Professor Sajad Haq. Sajad is a chief scientist in our area and works in a wide variety of advanced materials areas at Kinetic, including metamaterials and power sources. Sajad has very strong links with a variety of different academic institutions in the UK, and has particularly strong connections with the University of Surrey and Queen Mary University of London. So, Sajad, I know that you are talking to us not quite as directly as the other presenters, but via a speaker on a phone. But hopefully, Steve Morris has got you queued up and ready to go.
Perfect. Thank you very much, and hope you can all hear me. Yeah, apologies you can't see me. That's probably a good thing, to be honest. But I hope I'm coming through loud and clear. I have to make another apology. I am not the acoustics subject matter expert. He's kind of chickened out of this, so I've stepped in. So apologies for any of that. Okay, on to my slide 2. Okay, so I'll give a little bit of an introduction to Kinetic, who we are, what we do, say a little bit about some of the technologies that we are thinking about working in the acoustics arena, some of the applications as well, which I think might be a little bit different. Some crossover to some of the things you've already heard, some are a little bit different. We talk a bit about some of the challenges for metamaterials. You know, why bother with metamaterials? What do they offer up? You probably heard in the plenary some interesting comments from Arena, from Metaboard. I'll possibly add to that. And then finally, a few words of how to work with Kinetic. We're very keen on working with people, with academics, SMEs, primes. That's what we're all about. So I'll outline some routes in doing that. So next slide, please. So this is the introduction to Kinetic. Effectively, Kinetic was formed in 2001 when Mod split from DERA, which then got rebranded into DSDL, and then the other piece was Kinetic. So what does that actually mean? That basically means that Kinetic is not that mature a business. However, we do have a very strong legacy and history that we can bring to bear on current and future problems. We split up into a number of different capabilities. You can see those on the left-hand side. Advanced materials and manufacturing, obviously relevant to the metamaterial space, acoustic materials, etc., etc. Robotics and autonomy, power sources, as Pete mentioned. Human protection and performance is an important area for us. We like to keep the individual well screened and healthy, and acoustics has a role to play there as well. On the right-hand side shows you some of the sectors. We're probably, as a business, most famous for the defense and military markets, but that's not all we do. We have a very growing and thriving business in the commercial non-defense space. So infrastructure is really important. Energy and the environment are important areas that we're targeting, along with space. Space is a line of business that we directly feed into. Next slide, please. Okay, about 3-4 years ago, we set up effectively a unit, special ops unit, if you like, called Advanced Services and Products. That's effectively an incubator hub, which takes low TRL technologies through to the exploitation to market quickly. That's what it's all about. So, as you can see, it's all about doing it very, very quickly. We've had a number of successes over the last couple of years in doing that, and it's a way of operating that was not necessarily that familiar with Kinetic a few years ago, but it's something that we're pushing very hard and is key to developing technologies like metamaterials and getting them out to product quickly. Okay, next slide, please. Okay. All right. Some of the things that we do, R&D, clearly, product development are the centerpiece of Kinetic. In terms of materials, the portfolio is incredibly diverse. You name it, we tend to work in that area, but we do have a product focus because it's all about taking technology to the marketplace quickly, as I've said. We do provide advice and consultancy as well. That's part of our portfolio. We also have some fairly extensive facilities for measurement, testing, and evaluation and analysis. And I should say that a lot of what I'm going to show today relating to facilities, capabilities, expertise is actually open access. So any guys who want to tap into that, all you need to do is pick up the phone or speak to any of the Kinetic guys that will be around. Next slide, please. So this is an overview of what we do in the area of acoustics. So we have the capability across sort of the acoustic materials area, which includes metamaterials, but isn't purely focused on metamaterials, but is becoming an increasingly larger part of our capability. We have that expertise in the design, the development, and the integration of those materials. It's fine having the materials, but you've got to use them in a way that you can then turn that into product. Sometimes that might be for large platforms in the defense markets, or it could be for health devices or prognostic technologies. All of those things require some level of integration. We have also some fairly unique acoustic measurement and model facilities. A lot of those are bespoke. They're things that areas that we've been developing and continue to do so. And I'll give a little bit of an introduction to that as well. What's also really key in our area of acoustic materials is that ability to develop prototype solutions, but then undertake validation and testing. I'll talk a little bit about the validation and testing further along in my presentation, but it's really important to understand some of the challenges that new materials bring with regard to validation and testing. We undertake tech transfer. We also undertake training of people in some of these areas, as well as setting of standards. Our team is fairly multidisciplinary. It does consist of physicists, material scientists, engineers, acousticians, all sorts. And effectively, we pull that all together to give a holistic solution. Next slide, please. This starts to give some information on some of the things that we're involved in. On the left-hand side are just some examples of what were R&D programs, and actually some of this is going into product. But on the right-hand side, which is where I'm going to focus on for the time being, are some applications of areas of interest. So vibration and shock damping, for example, for engines or protective packaging, is really, really important. The acoustics of buildings, very, very important. And again, I've had a great lead-in from the two presenters previously, but again, really important. Communications, believe it or not, Kinetic have product for acoustic underwater comms. So the picture that you see on the top on the right-hand side is effectively a technology called STAR. It's a simultaneous transmission and receive, where we're using acoustic techniques to get a wide field of view and then undertake some duplexing with RF signaling. Human performance, really, really important to protect the individual. How do you protect them from vibration, from shock? How do you prevent their eardrums from excessive noise, for example? And it was enlightening to see the presentation from Gianluca, where he mentioned the cognitive effects of noise on individuals. So completely on board with that. Picture on the right-hand side there is a shoulder-worn acoustic targeting system. So that's effectively sensor-based technologies, which gives you information on projectiles that are heading towards you, the direction, the velocity, and effectively where that shot or projectile is coming from. So that's a product currently in our US division. The bottom the bottom picture there, IBDM, that's an international berthing and docking mechanism for the International Space Station that Kinetic is involved in developing. And there it's absolutely important, as you can imagine, that if you're trying to dock a spacecraft with the station, that you minimize things like shock and vibration. Okay, next slide, please. As I've said, we have a whole range of facilities. Now, those range from some of the traditional facilities in terms of materials manufacturing, materials testing, but we also have access to and host a large variety of facilities through some of our larger programs, some jointly with the Ministry of Defence, where we have got effectively things like the ocean basin or the towing tank or flight simulators. Again, some of these are relevant for acoustics, for underwater acoustics, for example, which is a large part of our business, and these are accessible. Next slide, please. So in terms of our acoustics work, what I've done is effectively laid this out in sort of four sections. So we do a lot of modeling and prediction. We develop some of our own tools which are bespoke to do the things that we need to do, are specific to particular applications or problem spaces. So we have analytic and we have numerical techniques. We also have COTS equipment as well, COTS codes that we use too. In terms of test and evaluation, that spans both airborne and underwater acoustics. There's work in the area of ultrasonics as well. So there's some pictures there of impedance tubes somewhere. Yep, impedance tubes, pulse tubes, large area towing arrays in a tank, mechanical testing, transmissibility rigs, etc., etc. Again, I can't emphasize enough, if anybody has a requirement for these, we're open to people approaching us to gain access to these facilities. Formulation and manufacture, I'll say a little bit more about that in my next slide, but if we have a whole range of manufacturing capability for small area R&D programs all the way to large area. And that can include layered manufacture, coatings, it can be bulk manufacture, it can be composite materials. So all of those things we have available at our fingertips in our laboratories, based in a number of sites, but predominantly on the Farnborough site. We undertake a lot of application and assurance studies as well. Next slide, please. Okay, metamaterials. So why bother is the question. And effectively what I'm doing is lining up everyone for some of the discussion sessions later on. So the reason that we're interested in metamaterials, because it does allow you an unprecedented degree of tailoring of the properties of metamaterials. You can do things with metamaterials that you cannot with other materials. Okay. One of the things that we've been looking at, for example, is the multifunctional behavior of materials and acoustic materials. Bottom left picture is effectively looking to gauge the hydrophobicity of materials so that we can actually undertake some cleaning of surfaces using acoustic energy. So a little bit different, but effectively that is promoted through that ability to be able to design a multifunctional metamaterial and then use acoustics in a slightly different way. So you can generally start using metamaterials for new applications. We're also looking at metamaterials for I don't know, let's call them mundane or more conventional applications, where metamaterials do offer advantage for things such as reducing the size and reducing the weight of materials. And again, you've seen that through the previous two presentations. But I guess for me, what really excites me is the ability to be able to start looking at and thinking about new applications where, for example, you're rerouting energy in predefined ways. If you were at the plenary from Sir John Pendry, he spoke about topological metamaterials, and all of that is relevant in the acoustic domain as well. In terms of some of the challenges, testing, again, Gianluca quite rightly pointed out some of the issues there. And, you know, we are working with people such as Metasonixx to understand some of the new testing requirements, some of the standards that will be necessary. So that work is ongoing. Another important challenge is, well, I've got the abbreviation there, ACQVV. That is Assurance, Certification, Qualification, Validation, and Verification. It's really, really important if you're going to take these material technologies into product, and depending on the application space, you will have to do some or all of that. And it can be very, very painful. And, you know, the reality is a lot of the aspects of some of the new processes, some of the new manufacturing techniques, and the materials that come out of them are not well understood. And that can potentially be a barrier to the exploitation of the technologies. And it's something that we're working with actually a number of primes where we're developing protocols to understand how to do that, and then passing that information on to the relevant industry providers. Fabrication, of course, is always touted as an issue for metamaterials. It's fabrication and scalability. Can you make things large enough and cheaply enough? There have been some significant advances. In fact, some of the pictures on that particular slide on the right-hand side is a very lightweight, very high performance acoustic metamaterial, which is of a significant size, shall we say. It is now possible to start doing things like 3D printing, additive manufacturing techniques, where you're using multiple materials, and you can do that over very large areas. Virtually every month, somebody announces a new piece of 3D equipment, and again, we're working very closely with some manufacturers to develop very large area additive layer manufacturing processes as well. Next slide, please. Okay, just a little bit more in terms of manufacturing. You do have the standard COTS techniques on the left-hand side. Everybody should be familiar with that. We've probably got something like 40 to 50 of these within Kinetic. Again, those are available if anybody wishes to use them. But more importantly, we have these bespoke manufacturing techniques. Some are shown on the right-hand side, which are almost where we're doing things like hybridizing different material manufacturing techniques. So we're ganging together things like bulk and thick film or thin film methods to give us the properties that we require, because we do not believe there's a single solution to a multi-materials problem here. We do work across all TRLs, that's very important, and I think I'm being flagged to hurry up, so I shall go on to my final slide, if I may. How to work with Kinetic. So, hopefully, one of the themes that comes out of this is that we've got a lot of stuff, but we want to share it with you guys. It is about shared access, because what Kinetic is about is prosperity for the UK and getting the technologies to the market quickly. Okay, we can provide case studies. We understand product development roadmaps. Okay, we can provide that safe environment to trial ideas. We understand requirements, technical requirements, because we have a very wide network, customer base. So, over, 300-400 suppliers we work with. We know what they want, and that's not just in the UK. It is global. We can work with you to develop the business cases, and we can help you access funding. We can do that directly or indirectly and across all TRLs. Okay. Basically, we have those routes to market. We can help integrate supply chains for you, take out a lot of the issues that a lot of businesses, particularly startups, face. We're there to help. So effectively, come and talk to us. We are on the other part, on the exhibition. So pop in there or come and have a chat anytime. And I'll finish there. Thank you very much.
Thanks very much for that, Sajad, and well done for doing it kind of remotely over the phone. And thanks also to Steve for flicking the slides. I think what we might do for time-wise is not ask any questions right now of Sajad, but wait until the end. And Sajad did flag up from the hub. There is plenty of opportunity to talk to him and other guys from Kinetic. I am seeing bits and bobs dribbling through from the hub, so we'll crack on so we can get to the Q&A at the end. The last talk is actually from me, and the purpose of my talk is just to sort of, so far we've had a predominantly acoustic focus from the sessions, and so I'm just going to very briefly address more of the thermal end of things by flagging up some of the areas that are of direct interest and ongoing interest to Kinetic. Hopefully you can all see my slide deck, and I'm sure I'll hear if you can't. The standard Kinetic front slide there, the wind turbines. The wind turbines actually is an area we developed and exploited some of our RF control technology, and that uses many of the tricks of the trade for RF metamaterials, and there should be a talk on that this afternoon. Let's see if I can change slide. Interesting. Oh yeah, here we are. There's a bit of a lag on my slide, so apologies if something flicks through. I work with a team of guys in the, I guess, the advanced materials area of Kinetic, and as Sajad alluded to, we have 3 very strong materials teams that fits very well with the emergent metamaterials technology area. We're a radio frequency team who look at things like microwave absorbent materials in different forms, such as paints, composites, even fabrics. Also, RF shielding is like the shielding in the acoustic and thermal domain, and an important technology area for us. Acoustic wise, well, Sajad's touched on that, but just to reiterate, we do a lot of stuff for sort of looking at materials to interact with sonar, some built environment stuff, and a lot of stuff to do with human health and safety and if you like, crew comfort. So an area of long-term interest for us. And then finally, we have my area, which is the electro-optic and infrared area, and that covers thermal technologies as well. We do all sorts of things, marking technologies and beacons, which I'll talk about a little bit, human vision, performance and protection, so protection from visible and non-visible radiation in the near-infrared and thermal infrared area, and even as diverse areas as anti-counterfeiting and document security. We are very fortunate to have a UK and certainly European unique measurement capability. We're also lucky that we do receive some MOD funding to support our measurement capability. But as is previously alluded to, we don't just look at military applications. We apply our technologies and kit to look at both commercial and defence areas. So we've got 4 little pictures there. So on the top right, we've got a very unusual bit of kit, which is based in the laboratory, and that looks at the scattering of radiation from surfaces. So we can measure how light scatters from surfaces in the thermal infrared, as well as the visible and the UV as well. That's pretty much unique in Northern Europe, actually. In the bottom left, we've got some of our portable equipment, which is used for an in-field thermal assessment. And here we've got them looking at a fleet auxiliary ship undertaking manoeuvres. So we can take measurements both at quite long ranges through all sorts of different atmospheres of platforms, and also we can take things close up and do more detailed thermography as well. Above that, you see a picture of a helicopter, and we can look for surface contamination in the thermal infrared and the near infrared. And so that's one thing the scientist is doing there. And we also develop new techniques as well. So we're interested in inherently multispectral detection and material solution. And the bottom right there is just an image that has been taken through some of our hyperspectral cameras. If you do have an unusual and interesting measurement problem, perhaps as to support your research or for a measurement of a product, as Sajad said, do contact us and we'd love to see if we can help. So I'm just going to talk very briefly about the combined acoustic thermal problem space. And I think I'll just relate a quick story I heard. I was talking to a guy who is heavily involved in the Australian mining industry, and they have a preference, at least in the Australian mining industry, to use female drivers for their heavy plant machinery. Female drivers in generally have been found to be drivers result in fewer maintenance issues for vehicles, fewer accidents, fewer wear and tear, just generally more considerate drivers. However, the vibration effects of these bits of machinery are absolutely significant. So you can result in numbing of nerves, shake up your digestive systems, even spinal injuries. And due to perhaps damage to or perceived risk to potential women's fertility, the Australian mining industry was sometimes asking people to sign disclaimers before they became drivers, or even discouraging women from driving these vehicles at all. So that's quite I think an interesting and focused problem that results in noise and vibration, particularly for mobile vehicles. A lot of the talks previously looked at the built environment, and that's clearly a massive exploitation channel for acoustic and thermal metamaterials. The space that I've most often dealt with in the past is actually looking at moving vehicles, which brings its own challenges. And I've definitely noticed that self-generated noise on platforms usually has a thermal component. A lot of engines are obviously air-breathing beasts that require cooling airflow and need to expel hot gases. We have running gears and exhausts, all of which generally contribute to a combined thermal and acoustic problem space. In terms of overall, the IR metamaterial solutions area that we're interested in, this slide has a list of the application areas that we're actively looking at. This spans from defence, so camouflage, through to sort of more commercial ID and marking. And because we work together with the acoustics team and the RF team, we know that many problem spaces are inherently multispectral or at very least dual band. So when we undertake, we might have a primary design requirement in perhaps the infrared, but we also look at the knock-on effect of the solution in other bands as well. Thermoregulation has been a pretty much constant theme of my career since I joined Kinetic back in 2002. I started at looking at trying to introduce passive cooling for vehicles operating in very hot desert environments. And I'm very interested in some of the recent technologies that have been published in looking at self-cooling materials. And there's a couple of pictures there taken from very recent publications. The most recent one is the science one at the top, which is essentially a metamaterial or disordered metamaterial media of microscopic inclusions in a polymer binder. The bottom one is a passive radiative cooling experimental setup, which is taken from a Nature paper in 2014. Generally, these materials have very common functionalities in that they need what we would call multispectral control of the emissivity. So a high emissivity in the thermal infrared spectrum where heat is radiated, so particularly 8 to 12 microns or so, and a very low emissivity in the visible and near infrared where the sun's output is at its strongest. So that is an area that is of active interest to us at the moment, trying to essentially achieve some benefit without putting more energy into a system to cool it. Other areas of interest to us include control of laser radiation, either through absorption or rejection. We have human vision experts, and a lot of the work we do is looking at laser eye protection. And that is another area where the emergent, in the infrared, where emergent metamaterial technologies might have a significant role to play. So in terms of metamaterials applications, one of the things we're interested in is marking and free space communications. And here we have 2 pictures of Kinetic products called beacons. Generally speaking, it was a class of beacon, and they have thermal emitters in the thermal infrared and the SWIR band infrared. We're interested in making these more selective, more discriminating, changing power settings, maybe even changing polarization settings at will. And Metamaterials offers a massive opportunity for that area. And what's nice and unusual perhaps for some metamaterial solutions we look at, they're not massive area ones as well. It's something that we can make in a small area. Slightly larger area applications are in the passive marking technology. Now, this is something that has been sold for a number of civil security marking markets and involves constructing essentially an ID symbol, which can be placed on the top of vehicles or on the side of vehicles that works simultaneously in the visible and the thermal infrared. And we can change the contrast in both bands at will. These are unpowered, and so and as long as they're outside, you will be able to see them. To explore these applications, one of the things that we did a few years ago now was build an example metamaterial structure to investigate opportunities for selective absorption and selective thermal emission. This is something that was based on one of the first RF metamaterial papers generated by Kinetic and the University of Exeter. And what we've done here is scaled it to work in the thermal infrared. At that time, you can see a photograph of the metamaterial in the bottom left there. You can see its size, it's about 5 millimeters square. And at the time we made that in the mid 2000s, that was a phenomenally large metamaterial surface. It was made by focused iron beam milling at the time. And that was as far as we could practically stretch our fabrication route. But to do that, doing that was very important for us, because it allows, as you can see from the data in the middle there, to fully characterize the sample, not only in terms of polarization, but also out to wide viewing angle. And I think the only thing I'd like to point out on this one as well, one of the impacts of moving to the thermal infrared, as you can see right at the bottom on the TM mode side, there's an additional mode there, a sub-fundamental mode, and that's due to the interaction of the Reststrahlen feature of the magnesium fluoride, which is the dielectric in the structure, and that's essentially a feature that's generated from the phonon modes in the structure. And that obviously highlights additional potential for spectral control in the thermal band that we don't see in the visible and microwave domains. So that was pretty much my last slide. Sajad has highlighted that we're very keen to talk to people with new technologies. We have a wide range of customers with very diverse requirements. We are receptive and keen to hear about novel metamaterial solutions. So, if you've got something we might be interested in, please do drop us a line. Contacts can be via the portal or hub or whatever we're calling it. And yes, the information's there, so please do have a look at it. Thank you very much.
Pete, I think we need to cover the questions now. Do you want me to?
If you don't mind, I'm not one of nature's best multitaskers, which I've been told, so I haven't been following the chat while I've been speaking. So
right. No, that's fine. That's fine. I'll read out what I've made a note of, and I'm going to do them in the order they were asked. So hopefully there'll be some sense to them. So I think after Daniel's presentation at the start, there were a couple of questions came in. So Daniel, you might want to pin your ears back here and listen to what this question is. How much area does it cover? Does it cover during installation? Does it target multiple frequency or single frequency? And what is the governing mechanism applied to your panels to mitigate the acoustic wave?
Yeah, thanks, Steve, for the question there. In terms of area our panels cover, we can use them in any type of conventional noise control solution. So freestanding barriers, enclosures, screens. It's effectively the same type of solution. It just works in a slightly different way. At the end of the day, the other side of the panel is just inherently quieter and much quieter at low frequencies compared to a conventional solution. In terms of our noise trap panels as well, it doesn't just operate on a single frequency or a small range of frequencies. We've actually developed the system to have a standardized off-the-shelf product that covers broadband acoustic waves. And our acoustic metamaterial performance is heavily focused from around 63 Hertz up to 800 Hertz. And what we actually get, because we construct our panels out of steel, you get the high frequencies for free. So you still get high frequencies performance due to the mass law contribution from the steel there. And in terms of how it works, we use a strongly coupled resonator array inside out to create the metamaterial structure. And that actually gives it a wave cancellation effect. So you have a phase shift of the incoming acoustic wave, which then gets cancelled locally due to the strongly coupled resonators.
Gianluca, did you want to say anything? Okay, fine. No, you're on mute, by the way, just in case you didn't know. The second question. I thought
that the question was for Daniel, so that's
well, it was said during his session, but I didn't know whether you'd like to add anything. I mean, it obviously won't relate to Daniel's technology, but just in general. That's fine.
That's okay.
Now, the next question is an interesting one. Do your materials work underwater? And if so, what impact would that have on the low frequency responses, as the equivalent wavelengths would be longer than those in air at a given frequency? I suspect that's something to do with underwater vehicles.
Yeah, it's a very good question. Theoretically, they should work. The physics is effectively the same, but it's something we haven't done here at Sonobex. We focus on airborne noise. But I have seen papers out there where they're looking at underwater acoustics to mitigate low frequency noise. Examples like drilling and piling activities underwater. So yeah, I think so. It is possible, but it's something we don't focus on specifically.
Yeah, perhaps that's the sort of question that ought to be taken offline, so to speak, because it's plainly confidential activity. So I would ask whoever asked the question to perhaps contact you direct or contact me, and I'll pass on the inquiry. That would probably be the best thing. And one, I guess, for all the speakers is, and this is an interesting one, is anyone looking at metamaterials for road surfaces? Cut down noise on road surfaces.
Yeah,
I think it just means you've got to put a new surface down, doesn't it?
We had an Innovate UK Smart Award grant a couple of years ago, which we developed an acoustic metamaterial based panel system for high-speed rail applications. Now, the noise of the high-speed rail is very similar to road noise. So yeah, we have solutions in terms of acoustic barrier, metamaterial-based solutions that we can use as screens alongside motorways, for example, road noise. And that's a relatively new product we've been developing there. So I'm happy to share further information if someone wants to reach out on that.
Okay, brilliant.
Can I add something here?
Yeah, please.
So we are working with Italian motorways to design panels, but I think the questions is interestingly on the asphalt. So can you actually put something, a metamaterial under the asphalt to mitigate the noise? If that is the question, there has been attempts in the US to do something in that direction, but then it becomes confidential, so please come back.
Yeah, okay, I've got that one. So whoever's asked that question, perhaps, if you contact me, my details are always available, easy to find. I'd be happy to put people in touch. Can you think of new functionalities with some time modulation of metamaterial surfaces? And Gianluca put in the box, we have looked at metamaterials that change on demand and objects like auto zoom lenses for sound. An interesting question might be what happens if we vibrate the MMT. So I don't know whether you want to enlarge on that, Gianluca. I mean, obviously they couldn't see the chat,
no.
So I've had to repeat it on.
So I tried to guess what the question, what the person who asked the question was thinking about.
Yeah.
And there is, of course, because we were talking about, also Pete was talking about multifunction metamaterials. Then there is an opportunity to think of what happens actually if you vibrate a structure. So a system which is already performing at a specific frequency or a specific frequency range, what happens if you vibrate it? And there are some interesting results in optics for this, and maybe there are transferable in acoustics. What we are looking at are instead what happens if the shape of the material changes and how this changes the performance, the acoustic performance of it.
Okay, thank you very much. We've got a few more questions. The next one's a bit contentious. I'm going to leave it till last just in case we can't cover everything. How do you, I think this is a general question, by the way. How do we manage the changes in material properties, thermal expansion, changes in dielectric properties, etc., with temperature in thermal metamaterials? And does this restrict them to operating in specific temperature ranges?
Well, I guess I'll have a go at answering that from Kinetic's perspective. I mean, the functionality of materials generally in RF, EOIR and acoustic as a function of temperature is very important. And so it's one thing that we do have equipment set up to characterize. And it's quite a wide range of different equipment to do that. Some of the environments that we have to work in range from quite high depths and pressures under the waters to low pressures at high altitudes, but also perhaps going very fast, so materials can go very hot. So you can get all kinds of funny businesses going on when you start changing the dimensions of the materials, particularly if they're resident, broadly speaking, at close to the wavelength operation, to use an electromagnetic analogy. You can get all kinds of funny things like moving waveguide modes, lensing, focusing. All of these things, if you've got a very challenging application space, need to be factored in and then modeled. So it's often these areas which can make the development of the new technology difficult, but it's something that you know, we do spend a lot of time looking at. Steve, you're on mute.
That, and then that becomes focused towards your specific application, and is effectively how it's dealt with.
Did you hear that? I mean, my microphone was on, and Sajad is still talking from yeah. Did we hear that?
I was answering a question. I think you're on mute, Steve. So I don't know if we've just been trying to answer the same question. But
did you hear what Sajad said?
I didn't. No, but I was talking. But yeah.
No, we didn't.
Right. Could you repeat that, Sajad? I do apologise. I'm not sure what quite.
Okay, yeah, no problem. Effectively, I was just adding to what Pete was saying.
Yeah.
And Pete is absolutely correct. What it boils down to in terms of a complex material system is understanding the trade space and understanding how you can manipulate that trade space, and then that relates directly into your application requirements, where you can start to prioritize, and that's the conventional way of trying to deal with those issues.
Did we all hear that? As I say, I can't tell because I've got the phone in my ear. So
Yes.
was that okay?
Yeah,
good. Yeah. Have metamaterials been investigated for thermal insulation applications?
Yes.
Excellent. So, so my suggestion is, whoever asked that question, get in touch with Sajad. He'll tell you all about it.
Indeed.
Indeed.
Yeah.
Yeah, if anybody needs to get in touch with any of the speakers, and you know, I'm happy to put them in contact. The last question I have is, I wonder what kind of new functionalities might be achieved with thermal and acoustic time modulated metamaterial surfaces. And brackets, I'm thinking of a non-reciprocal effects allowing, for instance, one-way thermal exchange, etc. I guess that's for you again, Pete, isn't it? Or for Sajad?
Sorry, so, I beg your pardon. Sorry, could you repeat the question?
I wonder what kind of new functionalities might be achieved with thermal and acoustic time modulated metamaterial surfaces. I'm thinking of non-reciprocal effects allowing, for instance, one-way thermal exchange, etc.
I mean, I think diodic effects are always of interest to us fundamentally. So one-way energy transfer effects, that's always going to have a great deal of interest, and particularly particularly in some of the military arenas. I don't think there's any sort of specifics I'd mention above that, but you know, certainly it is an area of interest to us.
Okay. Well, I don't know whether any of our presenters want to comment on anything that they've heard in terms of the questions, or indeed in terms of the other presentations. But we've got a couple of minutes left. I can give you the contentious question if you want it.
I think I saw that one. Bring on the mischievous questions. That's what I say.
Okay, so the mischievous question is, with all this expertise in crew comfort which is available, how did the MOD manage to spend billions of pounds on developing a new armoured vehicle which was unusable due to crew comfort issues?
Yeah,
well, I suppose.
I read those stories as well. So, I mean, I think really that would be a question better addressed by the MOD and the vehicle manufacturer. But yeah. I would say on a more general note that you know, we do have military users knocking on our door and saying, well, you know, our ride is a little rough for us, even to the point of loosening fillings and numbing bums and churning guts and things like that. What can you do to help? And so we've applied our vibroacoustic materials for a lot of those sort of real life problems. I wouldn't say we've necessarily used metamaterials there yet, but metamaterials are still an emerging issue for us. But we do have a very good grasp of what can be done with these materials, and we can make acoustic materials in very large areas as well.
I'm sure that the people who use these armoured vehicles would like to hear that, but it's just a question of whether you get the MOD to spend the money, isn't it? Perhaps.
Yeah.
I mean, I know we've only got a couple of minutes left. I don't know whether I want to admit that I'm the person who's organised this conference, because I'm scared that people might not be very happy. but yeah, I am the one who has actually organised it. So I'd just like to thank all the people who've spoken today in this session, and indeed all our support people. And I'd like to thank the people who've watched it. Obviously, I would reiterate that if you want to get in touch with anybody to talk any specifics on the questions, please do. My email address is Stephen, that's with a PH, .morris@ktn-uk.org. Nice and easy to remember. Just get in touch with me and I'll put you in touch with them. And as I say, thank you all for attending, and thank you the people who presented.
Yeah, well, as session chair, I'd like to just echo that sentiment. And personally, I found the talks today actually useful and fascinating. So thanks to Daniel, Gianluca and Sajad for those.
Excellent. Right. I guess we've come to the end of our time. Is that right? Yeah. I think that's the end of it. Yep.